Hello, and I would like to record this last lecture of Chapter 10 for a calculus-based Physics 2 class, and I would like to discuss today resistor and capacitor circuits, which are often called RC circuits. These are circuits which have both a resistor and a capacitor in them. We'll be looking at these circuits for only ideal batteries and in DC, that is direct current conditions, and we'll be focusing on the mathematics here because a separate video we've already taken a look at the intuition about how these circuits work. So let's go ahead and get started with this set of lecture slides. Okay, so what is a RC circuit? Well, it's going to contain both a resistor and a capacitor, as I already said. Let's have a look at the circuit diagram. Notice that there's an EMF source, which is a battery, a capacitor, which we'll label C, a resistor, which we'll label R, and there's a switch. Now, the EMF source, by the way, is capital Epsilon. The first phase of an RC circuit is when we charge the capacitor. So that's the first phase of an RC circuit. Okay? By the way, this capacitor, let's assume that the capacitance is set. We could maybe change the capacitance if we swap out a different capacitor. Let's assume this is an ideal battery, an EMF source, and even if the battery were to have real resistance, let's fold that resistance into this resistor. In fact, this resistor could be an equivalent resistance. It could be a resistor network. But for now, let's just consider it a single resistance. Okay? So the capacitor is initially uncharged. When we close the switch, the current will flow and the capacitor charge increases. And in fact, the capacitor will initially act like a piece of wire. Why is that? Because you can imagine that a capacitor plate is uncharged. And since it's uncharged, it is a conductor just waiting to be charged. As soon as there's push from the battery because the switch is closed, there's going to be current flowing from the positive plate over here to the positive plate, or you can imagine negative charges flow over here to the negative plate. But what really goes on is negative charges come off the negative plate and then move over here to the positive plate. So you can imagine in this particular case, the current is going to be, clockwise from positive towards negative. Okay? The direction of the conventional current. Notice the initial current, which is the maximum current, is given by Ohm's law. It's capital Epsilon divided by R, R being the resistance. Notice that? That's just the maximum value if the capacitor initially acts like a wire, so to say. Now, over time, the current is going to decrease. Let's think about why that is. Because when we build up charge on the capacitor, the current won't just go uninhibited as if this was a piece of wire. In fact, there's going to be charges in the way, and it's like crowding up a store. If the store first opens and everyone wants to go in, everyone goes in very quickly. But if there's already a bunch of people in the store, more people that enter the store progressively don't enter quite as quickly. So the current is not entering the capacitor quite as quickly as before. Okay. So you could imagine that the voltage difference across the capacitor at any time is the current charge in the capacitor, Q, divided by C, the capacitance. Okay? So that's solving the equation for capacitance for voltage. And when the capacitor is fully charged, the current should be zero. Because if it's fully charged, there should be no more current running. There should be no more flow of charge. And the capacitor voltage should be the same voltage as the battery. So it should be equal to the EMF. And Q now is not just any Q, it's Q max, the maximum charge on this capacitor based upon whatever the capacitance is. So you can imagine if you have more capacitance, you should have more charge stored up, because even if you have the same voltage, a greater capacitance is going to be a greater charge. So that seems to make sense. So this is the charging phase of the capacitor. Now let's have a look at the mathematics and be as specific as we can about charging this capacitor. So let us use Kirchhoff's loop rule for some time t. So for some time t, let's think about mathematically how these three components work together. The EMF source, the capacitor, and then the resistor. So the EMF source is a positive gain of voltage. The capacitor is being charged. So that takes energy away from the circuit, takes energy away from the battery, so that should be a negative. And then we're charging through the resistor, so based on the current, I times R is going to be the voltage drop across the resistor. So we get exactly this equation. The EMF minus Q over C, because that's the voltage drop across the capacitor at any moment, minus IR equals 0. So if we start in the lower right-hand corner and go clockwise, this is exactly what we should have via Kirchhoff's loop rule. That is to say, the voltage is uniquely defined. All the forces here are conservative. Solve this differential equation for the charge on the capacitor at time t. Now, by the way, in order to solve this, this is a first-order linear ordinary differential equation with a source term. So, in fact, the way you would actually think about this is in the following way. If you've ever had a differential equations class, maybe you are in a differential equations class now, a lot of times in a differential equations class, we see something like the following. So we see something like, let's see, y prime plus p of t, p of t, so this is p as a function of t, times y is equal to q as a function of t. Now this q as a function of t in this case will be epsilon, and then the p of t term is actually going to be 1 over c. That's a constant. It's not a function of time. It's actually a constant. And then what we're solving for is q. So let's let q be y. And then y prime will be dq dt. And dq dt is the change of charge with respect to time, which is the current. Now, by the way, I actually should have said this is 1 over RC, because we have to divide by R to get this derivative isolated by itself. And Q of t, will actually be epsilon over R. Okay, so hopefully you see that. Now again, I'm not going to solve this differential equation for you. Okay? This differential equation is somewhat difficult to solve if you've never seen the method, but otherwise the method is what's called an integrating factor. Okay? Maybe I'll show that as an addendum to this video. Okay? But that integrating factor, it turns out that way you can use the product rule and so on. You integrate both sides. And the equation that you get is this. You get Q as a function of t is Q max, which is epsilon over R, minus Q max, which is epsilon over R, e to the minus t over RC. Now why e? Because notice that in this equation, a derivative and the function itself are only different by constants, or just functions of time only, simple functions of time. So that suggests a natural exponential, namely Euler's number. Hopefully you recall that this special math number e is approximately 2.71. So we have 1 minus e to the minus t over RC times Q max out front. Now remember, Q max can be written as, let's see, capacitance times the maximum voltage across the battery, which is the EMF, epsilon. And then this RC has a very special name. It's sometimes called the time constant, sometimes called the E-folding time, sometimes called the characteristic time. Okay? By the way, notice that this equation looks like logistic growth. Because notice that when t equals 0, we'll be exactly down here, because you just have e to the 0 is 1, so 1 minus 1 is 0. So there's no charge on the capacitor. When t approaches infinity, notice that you'll have e to the minus infinity, which is 1 over e to the infinity, which goes to 0. So you just have 1 minus 0. So then you have Q max. So then the Q max is, again, C times epsilon. That's what we approach here. Now what about for some intermediate time? For some intermediate time, it's 1 minus some decimal times Q max. And so the curve should logistically grow. It should grow fast at first because of the exponential, but then slower and slower as the exponential gets closer and closer to 1. So getting closer to 1 minus 1. So again, this tau is not torque from physics 1. This is a time constant. It's often called tau. And tau is actually equal to R times C, resistance times capacitance. Ohms times farads should actually give you seconds. Okay? Now, by the way, I should quickly say this time constant, again, corresponds to an E-folding time. So notice 0.632 is the same thing as 1 minus e to the negative 1 power when t is actually equal to RC. That is to say, when we've reached 1 E-folding time, we're at about 63.2% of the maximum charge. Because again, this is 1 minus e to the negative 1 power, which is 1 minus 1 over e. Now, if you go 2 time constants from here to here, you'll notice that you'll be 1 minus e to the minus 2 power. So 1 minus 1 over e squared. And that should be, again, 2 characteristic times. And those are very well-known numbers, especially in computers and so on. Now, by the way, you may also say, don't we never get to fully charged? So mathematically, we never actually achieve this asymptote. Now, in practice, we usually go 4 or 5 time constants, and we're within less than 1%, and sometimes even less than 0.1% of the maximum charge on the capacitor. And we usually just say in practice, good enough. So we say that our instruments are only so accurate or only so good to measure within a certain threshold, and we reach that measurement threshold, we usually say that's when the capacitor is fully charged. Okay. Now, what if you wanted to know what the current was as a function of time in this RC circuit? Well, you would take the time derivative of this equation, because this equation is the full solution to this differential equation. So if you take the time derivative of this Q max times 1 is going to be 0. Because, well, the time derivative of a constant is 0. But then we have to take the time derivative of an exponential. So that's leave the exponential alone times Q max, and then the derivative of the exponent. That gives a minus 1 over RC. Now, minus 1 over RC times minus and Q max should exactly give this. So Q max times 1 over RC should be Q over RC. But wait a minute. Q over RC gives the following. So notice that Q max is C, which is the capacitance, times epsilon. But capacitance times epsilon over R, via Ohm's law, should be current. In fact, the maximum current. But then C over C, the capacitance terms, they actually cancel. So you just get epsilon over R, which we call I0, which is the maximum current. And then we've got e to the minus t over RC. Notice that the current, as a function of time, experiences exponential decay, where the maximum value of the current is epsilon over R. Now notice, again, the time constant, which is RC, now corresponds to just 1 over E. And 1 over E, remember, E is approximately 2.71 to 2 decimal places. But 1 over E to 3 decimal places is about 0.368. And 0.368 is approximately 1 E folding fraction of the maximum current. So notice that when we reach this characteristic time, we're about at 36.8% of the maximum current. Okay, I hope this makes sense. And keep in mind, this video should be merged with the intuition video about RC circuits that I've posted before. Okay. Notice also, if you have a smaller R or a smaller C, you get a faster charging of the capacitor. I showed that previously in the intuition active figure. Because if R is smaller or C is smaller, the time constant is smaller, it's quicker to charge the capacitor. And that should make sense, because if you have a smaller capacitor, you have less charge to put on the capacitor. But also, if you have a smaller resistance, the current is less inhibited. So the capacitor charges faster. Okay, how about if you discharge an RC circuit? So discharging a capacitor works in a similar manner. Notice the circuit diagram is even easier, because now we don't even have an EMF source. We only have a capacitor and a resistor. Now, by the way, let me just go a couple slides back quickly. Notice that a couple slides back, we saw that the positive charge was on the bottom, the negative charge was on the top of the capacitor. Whoops. So notice that previously, I think the current was running clockwise. In this case, the current is actually going to run counterclockwise. How do I know that? Because it's going to go from the positive plate towards the negative plate. In other words, that's going to be the direction of the conventional current. So the current's going to run not to charge the capacitor, but to discharge the capacitor. The capacitor initially has a voltage, V initial, of Q over C. Q is Q max, C is the capacitance of the capacitor, but the actual initial voltage is also typically just called epsilon, because it's the same voltage as whatever battery charged it. Okay? This resistance is R, so we're going to change the energy from potential energy to either heat or light energy, or maybe some other form of energy, maybe even mechanical energy. Because this is a resistor. It could be a light bulb, that would be electromagnetic energy. It could be a toaster, which would be heat energy, or it could be like a fan, so that'd be mechanical energy. Okay? But anyway, we're going to change the energy form. Now, what happens when current starts running? Well, when current starts running, again, it's going counterclockwise. We're discharging the capacitor. At first, the capacitor acts like a battery at the first moment. Why is that? Because as soon as you connect the switch, the charges say, wow, we were going to go from the positive to the negative plate very quickly. It's like if there's a fire in the store, if I go back to the analogy. If there's a fire in the store, you can imagine that, at first, the number of people that exit is very rapid, but then over time, fewer and fewer people are exiting, only the stragglers. Also note that once this capacitor starts to discharge, it's going to be less rapid. There's going to be less electrostatic attraction from the positive charges to the negative charges, so the current should be less over time as we discharge the capacitor. But also the charge should decrease over time, and in fact decrease exponentially. So the initial current, being the initial voltage over the resistance, is the maximum charge over RC. And as the capacitor loses charge, the voltage decreases and the current decreases. The final charge and the final current are both zero when fully discharged. In other words, there should be horizontal asymptotes at Q equals 0 coulombs and I equals 0 amperes. So now let's look at the mathematics. Let us use Kirchhoff's loop rule again for time t. Now notice we're going to do minus Q over C minus IR, because we're going to be losing energy from the capacitor and we're going to be losing energy from the resistor, both. So when we go across this resistor, we lose energy because we're going with the current. But now when we go across this capacitor, notice that the capacitor electric field is in the opposite direction of the current. And since the capacitor electric field's in the opposite direction of the current, that gives minus Q over C. Again, another way to think about this is we're losing energy across the capacitor. Now, this differential equation is actually much easier to solve because this differential equation is going to be something like this. It's going to be something like if I, let's see, if I divide by negative R, so if I divide by negative R, we've got, let's see, Q over RC plus I equals 0, and that's the same thing as dq dt is equal to minus 1 over RC times Q. Notice this is a first order linear differential equation with no source term, and it's actually separable. So separable means you can move the dt over to here and q over to here and just directly integrate both sides. Now, many of you should have hopefully seen this before in a Calculus 1 class. So I'm not going to go through the full solution here because for those in my Calculus Base 2 physics class, I'm going to actually give this problem as part of your final exam. Okay? So fair warning, you should be able to solve this differential equation using first order linear separable differential equation methods from Calculus 1. Okay? So expect that on your final exam. I'm saying that. Okay? But those of you that may want to work it out, you solve the differential equation and you get this. Q as a function of time is Q times e to the minus t over RC, and that Q is Q max, and Q max was C V0. Notice that it's just the charge is exponentially decaying with time, and that's exactly what we expect from this differential equation. Okay, if you want the current, you can take the time derivative of this equation. So you get CV0 times negative 1 over RC. The C's cancel. V0 over R is the maximum current. Notice the only reason we have a minus is the minus suggests that the current is in the opposite direction of what it was before. The current in this circuit diagram is counterclockwise as opposed to being clockwise what it was when we were charging. Okay? So both the voltage and the current follow this exponential decay trend. Notice again, here's one e-folding time, here's two e-folding times, and so on, and the e-folding time, which again is called the characteristic time or the time constant, is still equal to RC, because RC is what modulates this time in the exponential of this curve, if you will. Okay, I hope that kind of makes sense. So again, a smaller resistance or capacitance, even when you're discharging, is a faster discharge of a capacitor. I've already shown this active figure in the intuition video. Okay, let's discuss this time constant in a little more detail. I've already kind of said these out loud, but just to give you a slide on this, a lot of times tau is written with the subscript RC because it's the RC discharge time constant. 1 minus e to the minus 1, which is 1 minus 1 over e, is about 63.2%, 0.632. We saw that before. Ohms is volts divided by amperes. Farads is coulombs per volt. Notice the volts disappear. You get coulombs per ampere. But wait a minute, an ampere is a coulomb per second. So coulombs divided by coulombs per second is seconds. And so the time constant is in units of seconds for SI units. Now, 1 over E is about 0.368. So again, that's when we're exponentially decaying, you get to about 1 over E. All right, in other words, the time constant, the capacitor loses, in one time constant, the capacitor loses 63.2% of its initial charge. That's because 36.8% of the initial charge is remaining. Now, what about applications of RC circuits? I think I mentioned some of these in the intuition video as well. A camera flash stores energy in a capacitor in what we call a flash circuit. When the flash goes off, energy is discharged very quickly through the bulb. You discharge very fast because the resistance of the bulb is quite small. Okay, so here's a circuit diagram where you only have a capacitor and a resistor, and the resistor is the light bulb filament. Now it takes the battery a few seconds to recharge for another flash. So if you have a battery, a resistor, and a capacitor, okay, notice that with the battery has some internal resistance, okay? But the charging is slow because the internal resistance of the battery is actually going to be much larger than this light bulb resistance, okay? So think about this. Real batteries have real internal resistance, and because the internal resistance of that real battery is much larger than the light bulb resistance, it takes a little while to charge that capacitor before you take another flash photograph. So you can't just take one flash photograph after the next if you're using a camera or, let's say, a smartphone. It takes a little while to charge that capacitor again. Okay? Now, again, a rainy day RC circuit is when you're changing, say, the rate of your windshield wipers. Okay? When you adjust the dial control, the delay of the intermittent windshield wipers in your car, you're adjusting a variable resistor in an RC circuit that triggers the wipers. Okay? And notice that if you increase the resistance, you increase the time constant. This is a longer delay between the swipes of the blades. So a light mist calls for a large time constant and thus a large resistance. Whereas a heavy downpour calls for a small resistance and a small delay because you want the wipers to engage very rapidly. So I'll show this example in a later video, but again, a heart defibrillator is, again, another RC circuit device. And the resistance is basically through the patient's body. And the capacitors are charged with those paddles. Okay? So, thank you very much for your attention in this video. Please smash that like button if you like this content, and please subscribe to the channel to grow the channel. Please share it with people that you know that could benefit from this content. And I want to thank you for your attention in watching this video. I will see you in the next video. Thanks for watching.